And finally, homework problem number 27 from section 7.4. We have in our numerator a degree 3 polynomial. In the denominator, altogether it is a degree 4 polynomial. So we are ready for fraction decomposition. Our denominator has two quadratic factors that cannot be factored in the real number system any further. So that means that this fraction is equal to sum of rational functions with denominators x squared plus 1 and x squared plus 2. I'm emphasizing the parentheses, they're not needed there. And if I have started with a lesser degree polynomial numerator to its denominator, then as I do fraction decomposition, I have lesser degree polynomials above my quadratics, so I have linear. Unknown a, x plus unknown b, unknown c, x plus unknown d. A, b, c, and d are constants that we are going to find. So the equation of this integrand being equal to this sum, I'm going to take that equation and multiply by the denominator of x squared plus 1 times x squared plus 2. So the left side turns into just the numerator of the integrand, and the right side of the equation has ax plus b multiplying to the x squared plus 2 plus a cx plus d multiplying to an x squared plus 1. Now, if I want to find what a, b, c, and d are, it's going to be easiest if I go through expanding the polynomial on the right. So I have ax distributing through, giving me ax cubed plus 2ax. And then I have b distributing over, giving me plus bx squared plus 2b. And then this plus sign. And now cx distributed, cx cubed plus cx. And then d distributed plus dx squared plus d. I need to figure out what is my coefficient for x cubed, what is my coefficient for x squared, what is my coefficient for x, and what is my constant for this right polynomial. And now I'm looking at, for x cubed, I have ax cubed plus cx cubed. So a plus c is the coefficient for x cubed. For x squared, I have bx squared plus dx squared. So the coefficient for x squared is b plus d. For x's, I have 2ax plus cx. So 2a plus c is my coefficient for x. And anything left over should not be multiplied by x, so it is part of the constant term 2b plus d. And now I have the coefficient of x cubed on the left side is 1, and it must be equal to the coefficient of x cubed on the right side, which is a plus c. Next, the coefficient for x squared on the left is 1. On the right, the coefficient for x squared is b plus d, so 1 must equal b plus d. Next, the coefficient of my x term is a positive 2 on the left side of the equation, and on the right side, it is 2a plus c. And finally, my constant on the left is 1, and it must equal the constant on the right, which is 2b plus d. Now I have 4 equations with 4 unknowns, but conveniently, I have pairs. I have an equation and another equation that involve only a and c. I can group those together. So, grouping those together, I have that I'm going to bring this equation over here, and I'm going to subtract the 2 equations. 1 minus 2, a minus 2a, and c minus c ends up being 0. My a must be equal to 1, and then if a is equal to 1, and 1 plus c equals 1, my c must be equal to 0. So I've got my a and my c. The other pair of equations are involving b and d. I'm going to bring this equation over and subtract. 1 minus 1 is 0. 2b minus b is b, and d minus d is 0. So I get that b must be equal to 0. If b is equal to 0, d must be equal to negative 1. And now I'm going to take those constants and rewrite my integrand as a 1x plus 0, or just x, over x squared plus 1. And then I have cx plus d, which is 0x minus 1, so just negative 1, over x squared plus 2. And these are both really nicely going to be just u substitution. For my first term, my u is going to be x squared plus 1. Or I should say the first integral is going to be u substitution. The second one is going to be trig substitution. My derivative is 2x dx. I divide the 2 over here to the du, and then I can see that the x times the dx is replaced with a 1/2 times du, and I have the integral of 1 over u. I'm getting 1/2 natural log of the absolute value of u, but I don't need those absolute values when u is x squared plus 1, because x squared plus 1 is always positive. Now, for this second one, I'm going to write minus, and then I'm going to focus in on the fact that I am working with dx over x squared plus 2. With trig substitution, I'm thinking about what is the function being squared, what is the number being squared, that are brought together in an addition or subtraction relationship. If I'm going to get an addition of those two, they need to be the legs of a right triangle. If the x and the root 2 are both legs, then I'm either going to use tangent or cotangent, and I would prefer tangent. Tangent is equal to the opposite side divided by the adjacent side, and then Pythagorean theorem gives us the square root of that sum of squares that we have. When I'm doing the trig substitution, I've got my u, and now I need my du, so basically I need to take the derivative. Derivative of tangent is secant squared theta, and I need to multiply by the differential d theta. The derivative of x divided by root 2 is 1 divided by root 2 multiplied by the differential dx. Dx will be substituted with multiply the root 2 over here. Root 2 times secant squared theta d theta. For x squared plus 2, I can choose to solve for x and bring that in, or I can also choose to look at my triangle and say the side that was completed through Pythagorean theorem divided by the side that is just the constant that was being squared gives me hypotenuse over adjacent. The hypotenuse over adjacent must be equal to cosine's reciprocal, which is secant. And if I want to know what to replace x squared plus 2 with, then I'm going to square both sides. And multiply by 2. And now I can see that I will be substituting my x squared plus 2 with 2 times secant squared theta. And I'm ready for my big giant substitution. The dx is replaced with root 2 secant squared theta d theta. The x squared plus 2 is replaced with 2 times secant squared theta. And then this simplifies to just root 2 over 2 d theta. When I integrate, I get root 2 over 2 times theta. And then I need to go back to the original variable. If I look at my quote u, then theta is equal to inverse tangent of x over root 2. And that then finishes up what my integration was when I bring the two of those together. And all I need is plus c, and we have finished that integration. Yay!